Hey everyone, we're here with Matt, CEO of Blocknative. He'll be doing a talk on Share the MEV, recirculating proceeds to all the right places. And I'll let him take it from here.
Thanks, Shinju, and thanks everybody for having me. We're going to spend the next 20-25 minutes talking about sharing the MEV in a post-merge, post-block building world. I'll go through things fairly quickly, and then if you have questions, by all means put them in the chat, or you can always find me on Twitter at @mcutler. So hey, big news flash, the merge has arrived. That happened just a few weeks ago, which is super exciting. And it was by far the most significant and substantial upgrade to the network to date. We obviously, the big headline feature, of course, was the transition at the consensus layer, moving from proof of work to proof of stake, and saying goodbye to energy consuming GPUs securing the network. But also there are many more fundamental upgrades to the network that don't quite get as many headlines, don't quite get as much attention, that in many ways are as important as the consensus layer upgrades. In particular, the network was very much moving from being a monolithic network where sort of a small number of actors did everything to a much more modular network, which allows for deeper levels of decentralization at many areas of how the network itself operates. Second, the other thing to know is many people feel like the merge was a destination, like we're finally here. It's not a destination, it's a milestone on a journey. And that actually the merge is one of a series of named upgrades that all rhyme, of course, the merge and the surge and the verge and the purge and the splurge. And each one of these are planned significant upgrades to the network. It can be difficult to remember sort of what these are all about, but there's actually some very simple mnemonics here. So the merge was merging the proof of work chain with the proof of stake chain. The surge, the S here, stands for scalability. It's a bunch of upgrades and changes to enable next levels of scalability. The verge, the V, talks about the transition from Merkle trees to Verkle trees. This is basically making the network more efficient and improving data availability. The purge, the P in purge, stands for pruning or removing old data from the network, so that you don't have as heavy data storage requirements. It's faster to sync, and not everybody needs to know everything all the time. It just becomes easier and more efficient to operate the network. And then the splurge is sort of everything else that doesn't fit into the above. And that's not to say that those things are less important. In fact, in many ways, the contents of the splurge are dependent on some of the upgrades that are happening in the merge, surge, verge, and purge. So pretty fun that this is a very rich product roadmap, and that, you know, not only as Ethereum reached major development milestones, it has significant major milestones in its future. Now, really what the merge was about setting the foundation for future scalability, effectively positioning Ethereum to be the foundation of the next economy, while preserving and even enhancing decentralization. So often in Web3 systems and blockchain systems, there's an inherent trade-off between how fast you want things to work, how scalable you want things to go, and how decentralized they are. The easy way to scale a Web3 system is just, you know, up the level of compute required. So to operate on the network, rather than using a small consumer grade laptop or even a Raspberry Pi, you just require, you know, a giant AWS instance, which actually does improve throughput, but means very few participants can actually be a part of operating the network. And so the merge is all about the necessary upgrades that allow huge scalability enhancements without making steps backwards as it relates to decentralization network participation. The economic rewards changed significantly. So under proof of work, we had block rewards, gas fees, and MEV. But those had very significant negative externalities, meaning to participate in proof of work, you needed specialized compute. It was power intensive. Most people didn't want to operate machines under their desk for long periods of time with nothing happening, and maybe once a year or less often than that, you might get a payout. So then you join mining pools to sort of even everything out. So what wound up happening was most of the mining power on Ethereum, also true of Bitcoin, got consolidated into a relatively small number of mining pools. So you were part of a pool that was quite attractive if you were a miner because it allowed you to sort of smooth out your returns. But it had this negative consequence of much of what you did was dictated by the mining pool operators, sort of the owners or leaders of those pools. And so effectively a pretty small set of actors who there wasn't a lot of visibility into actually had a lot of decision-making power over what would go on the network. And so this is not great as it relates to centralization of the infrastructure and centralization of control. And so one of the big focuses of the merge was to introduce deeper levels of decentralization to prevent some of this type of stuff from happening. Now, when we move the consensus layer from proof of work to proof of stake, there's a bunch of significant changes, right? We go to a game theoretic model of staking versus a cryptographic model of proof of work. It can be performed on commodity low-end hardware. It enables what's known as client diversity. So there's actually 6 different software packages that implement the proof of stake protocol and that are widely deployed. So there's not one client which really owns and operates the network. This is important because if there's a bug in a specific client, that bug, if that client is dominant on the network, then can create all sorts of real headaches down the line, or there's corruption in that client. And so by client diversity, you reduce the risk of a single point of failure at the network layer. What's nice about proof of stake is you don't need computers or you don't need power to secure the network. Instead, the base asset itself is what's securing the network. So ETH is securing Ethereum, and it's highly self-referential with fewer negative or fewer externalities associated with it. It also enables things like liquid staking. So to operate a staker, you need to operate a validator as a staker, you need 32 ETH, which is a pretty high bar. 32 ETH is a lot, but realize the original specifications for proof of stake was 1,500 ETH per staker. So it's come down a whole lot. The liquid staking basically allows you to participate in staking with less than 32 ETH and to move your stake around. And there's multiple providers out there of liquid staking. And then ultimately, it's just easier, cheaper, and simpler to participate in the network and to facilitate decentralization. And this is many of the goals and objectives of Ethereum proof of stake. Now, the economic incentives change here. So because you don't need specialized computers and because you don't need a lot of power to operate them, the block rewards or new issuance under the merge and under proof of stake go way down. It's a fraction each day. Vastly less ETH is being generated by the network than was happening previously. Interestingly, a lot of folks felt like, oh, the merge is really going to improve gas fees. Well, actually, gas fees are a function of block space and demand, and the merge really didn't change anything there. That wasn't part of the merge upgrade. So gas fees are effectively unchanged. It's kind of unchanged. It's sort of interesting that the merge happened at a period of relatively low network congestion. So gas fees are already pretty low. Merge goes through, gas fees stay pretty low. It introduces this new idea of slashing that didn't exist before. This is sort of key to the game theoretic model, which is if you are the validator who is at the tip of the chain, you get the opportunity to propose a block. You're known as the proposer. If you basically follow the rules, you're good and you get a reward. But if you play games like you propose multiple blocks to the network during your slot, you're at risk of slashing, which is getting your stake reduced. So there's benefits for being a good actor, and there's serious negative consequences for not being a good actor. And then MEV. So with lower block rewards and flat gas fees, MEV as a percentage of return goes way up. And so MEV was sort of a background element in the proof of work model. I mean, it's certainly there and talked about, but it comes much more to the foreground in proof of stake as a form of incentive for folks who are validating on the network. And so this is where now, as a result of the merge and some of the changes that happened there, MEV is really a mainstream conversation in the Ethereum ecosystem. MEV is this notion of what was originally termed miner extractable value, but now, of course, we don't have miners anymore, and it's not just miners who can extract this value. So the definition has been expanded to just say maximum or maximal extractable value. That's MEV. And what this is value derived from controlling transaction inclusion and ordering. So in any transaction system, Web3 or otherwise, that's ordered. So by the way, you can't really have a transaction system without ordering because you need to know the order of operations, a sequence in order to settle properly. All transaction systems have ordering, and it turns out that ordering matters, as in which transactions get included and the order in which they get included. There is value that can be extracted as a consequence of that. And this is the broad term of MEV, value derived from transaction inclusion and ordering. And under the world of proof of work, miners and mining pool operators were the small cabal who actually form block templates or the contents of a block. These mining pool operators determined which transactions got into a block and in what sequence. And they were able to manipulate that and to extract value from doing so. This was starting to happen. It's perceived as really sort of dangerous for the network if it wasn't open and transparent. A project came along called Flashbots that helped sort of open this all up and make it more transparent and programmable. It also accelerated MEV extraction in many ways as well, but basically brought it out into the open. Now, under the world of proof of stake, you don't have miners anymore who are setting block ordering. You have validators who are the tip of the chain. And when you're the tip of the chain, you can propose a block to the network, which means you can decide, if you're the validator, the tip of the chain, what transactions go in and in what order. And that allows you, and that puts you in position to extract MEV. And there's a whole bunch of consequences to that. Now, MEV and Ethereum is a pretty big deal. It's growing pretty rapidly, and some of these charts are a little moving, but low-end estimates in the billions of dollars of value. And to give you some examples of what this looks like, here are some examples of like transactions ordering based on gas fees. This is a naive form of block construction. You take all the transactions of the mempool that have been submitted, and you say, we're just going to order them stack ranked by gas price. The transactions at the highest gas price go at the top of the block. The transactions at the lowest gas price go at the bottom of the block. You might want to do something like arbitrage. And so arbitrage says someone's going to do a trade that's going to move the price on a certain decentralized exchange, and there's going to be a price discrepancy between exchange A and exchange B as a result of a transaction happening. And if I can slide a transaction immediately behind the target transaction, not 2 or 3 spots down or 10 spots down, but immediately thereafter, I know I can lock in profit margin. I can extract the price difference that has resulted, and I get a reward for having done so. So this is where this preferential transaction ordering of MEV comes into effect. There's a target transaction that's going to move a price. There's an arbitrage transaction that needs to be placed exactly behind it, and there's value in that placement. Similarly, then there's obviously externalities associated with here where people compete on latency to try to get right in there, because this was, when we were dealing with prior forms of the network, time really mattered. Or if there's more randomness that can introduce, you'd have transaction spam. So without structured ways to specify ordering and ordering preferences, you have lots of problems on the network like latency wars and transaction spam. Similarly, you have front running. So there's a transaction that's going to happen. Hey, if I can get just in front of that, I can extract some value for that. So I want to slide my transaction in just ahead of the target transaction. And again, this creates gas wars. People compete for front running opportunities. And then finally, sandwich attacks, which is putting transactions just before and just after a target. So for instance, there's a trade. I put a transaction before. I'm going to move the price up a little bit. The target trade is going to happen. It's going to move the price even further. And then right behind that, I sell what I bought before and I pocket the difference. Now, the challenge here is that the target transaction actually gets less favorable settlement. So you actually experience slippage or less favorable terms of settlement as a result of being sandwiched. And that's a big negative externality as it relates to this form of MEV. You could also imagine things like suppression ordering, where you're basically going to put transactions in that displace a transaction that would otherwise get in, and that is obviously censorship. And so these are all forms of transaction ordering attacks where value can be extracted from the network. Okay. Now, there's this notion of the MEV supply chain where a user has intent to transact. They compose it in a wallet, they sign that transaction, and they send it to the network. The searcher then inspects that transaction, and if they're able to find one of these opportunities, they create a response bundle. So one of the things that people don't always understand is that MEV and searchers actually add new transactions to the network that wouldn't normally be there, consuming block space, right? They give this transaction this new actor called a builder. So a builder under the world of the merge is a specialized group of actors who construct blocks on behalf of the network and then pass it forward. In this case, it's called a miner, but now it's a validator, okay? Now, as we think about this as Blocknative, we think about where does the transaction originate? A user decides to do something. They use a wallet and a DApp protocol, exchange or marketplace underneath the covers, but they're the ones where that source, the origination of the transaction, where the MEV comes from, but that they don't participate in any of the value that gets created. In fact, users are neither aware or informed that something's happening with their transactions. And it doesn't seem very equitable that the user does something that creates value, and because the user either doesn't have access to information or the user is not sufficiently sophisticated, they're cut out of, or they suffer, in fact, even less favorable settlement. And so we think that the current state of affairs is not great in terms of from outside observability, in terms of the equity of the network, and that the value flowing downhill in the supply chain, where it starts with the user but ultimately accrues at the end, is not ideal. Okay, and so, by the way, you can look at this stuff with services like Zero MEV, where here's an example that's highlighted here in red of a sandwich attack where there was $1,800 impact on the target transaction. This is the sort of stuff that's happening. Now, enter this notion of proposer-builder separation. I mentioned that briefly. It used to be the mining pool operators who are responsible for constructing blocks. But with the merge, we also introduced PBS, or the first versions of PBS, that split apart block construction from block proposal. This carries many benefits to it. PBS counteracts natural validator centralization. So imagine you have a large validator set. They have lots of ETH. They operate lots of validators. They have high rates of return. They have a lot of resources. These entities can start to get smart and good at MEV extraction, and that makes them build more profitable blocks that return a higher rate of return, that allow them to collect more ETH, that allow them to create more validators, that allow them to build more of this. And so this puts big centralized validator pools and staking pools at a distinct advantage to lone independent stakers, which creates the conditions for validator centralization and of consolidation of staking resources. And so one of the big benefits of PBS is it allows a solo staker, home and independent staker, to be as profitable as any large pool. In doing so, what you do is you massively reduce the amount of compute requirements that it takes to operate a validator. So now a validator is a very simple, lightweight piece of code that doesn't require much in terms of compute or bandwidth or storage. It specializes and enables efficient MEV extraction, and the net result of this is significantly increasing rewards and therefore staking yield. And what also has this interesting characteristic of is creates the opportunity for a new class of actor to contribute a whole bunch of resource-intensive infrastructure, namely in the form of compute and data availability, to the network. So the network gets stronger because there's now new actors in the network who bring high degree of infrastructure resources that wouldn't have been there otherwise in this role. And that fundamentally what this does is enables modularity at the execution layers. We talked about this notion of modularity before. So block builders like Blocknative are a new class of network participants. It's a competitive marketplace, so block builders compete with each other for the chance to win the next block, and it enables programmable or expressive block construction. So part of the big benefits of moving towards modularity is you move towards programmability, you move towards folks being able to express preferences at different layers of the stack and ultimately see different behaviors at different layers of the stack as well. So today we're seeing a lot of what are known as max profit blocks or max extractive blocks, but there's also actors out there who are producing what they call ethical blocks or non-malicious blocks. There are many regulatory compliant blocks that are happening as well. In the future, we may see things like green or sustainable or carbon offset blocks. You may have this notion of fair ordered, which is put in quotes because it's not totally clear that that's even possible, and all sorts of other forms of block. I was just talking to someone about geographic blocks that have certain restrictions on where the validator sets are physically located for various reasons. And so this is all stuff that we think is coming and quite interesting. It's kind of like a cupcake, depending on which way you slice it, top to bottom, left to right, up to down, you might get different results. Now, one of the interesting things is sort of what is the source of this MEV? It's transactions and users. And what we think is really compelling about some of the programmability aspects of block building is that this economic value could flow back to its source. So, hey, what if under proof of stake in block building, value could flow back and be shared with users' wallets and dApps? We think this would be quite constructive so that you have more equitable distribution of MEV throughout the supply chain, and you have folks being able to express their preference about where MEV gets routed from the very beginning, from the user themselves and the tooling that they're using, all the way through the supply chain. We think that now is the time to begin preparing for all of this. Obviously, the merge is here. Value recirculation is just starting to get going, but quite frankly, that there's still a long way to go. And there's some very specific action items that if you're interested in value recirculation, that you can begin to adopt. So basically, we at Blocknative provide real-time mempool data that's very easy to integrate via real-time APIs and well-established in building stuff for 4 years. And that can facilitate more effective and more complete transaction competition. We can provide capabilities that enable more accurate gas estimation, previewing transactions, providing MEV awareness and transaction monitoring. That's what we do. And blocks are basically built in the mempool. And what we're effectively trying to offer to the ecosystem is a block builder's toolbox. As we think about various sources of centralization in the network, there is concern about centralization of the block builders themselves, and having more block builder diversity, more participants in the block building network, we think is going to be ultimately healthy for the state of Ethereum, and we want to enable other block builders to do so. And in fact, many of the top block builders that are out there today are using Blocknative infrastructure in their operations. We have a whole bunch of real-time infrastructure you can learn about on our website. We have our Mempool Explorer, an API that allows you to sort of see this stuff in real time. There's a bunch of interesting relay capabilities that we have. We operate the what's called Dreamboat, one of the relays in block building. You can read the docs, open source GitHub, and see our uptime dashboard just by scanning these QR codes for those watching along at home. And we're just really excited to enable recirculation of MEV and sharing the MEV in the ecosystem. And that's what I have to share with you today. I know move very quickly. There's a lot to cover in this topic, but it's an exciting topic, and it's one that we think is relevant to the ecosystem.
Thanks, Matt. This was great.
Thanks, everybody.